Good morning, everybody. Welcome to our Global Future Alliance International Webinar Series. Due to some unforeseen last-minute obligation, Dr. Attilio Toscano is not able to join us today. So instead, Dr. Stevo Lavrnic, he's a senior researcher in his team, has kindly offered to step in and present their work at the University of Bologna. So Dr. Lavrnic is also an environmental engineer, and he's currently a senior assistant professor at the Department of Agri-Food Sciences and Technologies at the University of Bologna, where he has been carrying out his research activities since 2017, focusing on the agricultural water management and sustainable use of water resources, with particular interest for nature-based solutions and wastewater reuse. So I'm happy to invite Dr. Lavrnic, and I'm so happy and delighted that he's able to step in and present their work at the University of Bologna. Please go ahead, Dr. Lavrnic, and share your screen.
Thank you very much for the introduction. Yes, Professor Toscano is really sorry he can't join, but it was the last minute urgency, so it happened like that. So I will be telling you today about our experiences at the University of Bologna regarding water and wastewater management and reuse for agriculture. We are a Department of Agriculture, so we are dealing with water management in agriculture mostly. That water management includes different sorry about that. Water management includes different areas, but we are trying to make it more sustainable. So just the brief introduction of the group. We are Agriculture, Hydraulics, and Watershed Protection Group. We have different areas that we are focusing on. So we are working a lot on wastewater treatment mostly through nature-based solutions and reuse of treated effluent. We also deal with the optimization of the irrigation water use, and finally about water quality protection. The director of the group is Professor Attilio Toscano, and we are different people in the group. As you can see, it's not a big group, but it's a well working one. So I'm assistant professor, and I'm working with Professor Toscano on basically most of all the projects we have. So just a brief introduction of the Nexus concept in the case you're not familiar with it. Lately, especially in European Union, so the European Commission is pushing a lot on considering Nexus approach. So considering different environmental components that have the role in the management of different areas. So if we talk about agriculture, it's mostly water, energy, food. Nexus lately we are adding also ecosystem components. So water, energy, food, and ecosystem component, you will realize that they are all very interconnected between them, and we cannot focus only on water or only on or food without considering other components. And this Nexus approach is crucial to achieve food security and sustainable agricultural production, especially in the context where we have growing demands and where we have low water availability. We know that agriculture is the biggest consumer of water in the world. It's around 70% on the world level. In Italy, it's a bit lower than that. In Italy, it's around 50%, but the whole Mediterranean area, so south of Europe, North Africa, Middle East, the average percentage of water used for irrigation is around 80%. So it's quite a big portion. This is very important in the context of climate change. So Mediterranean area is one of the hot spots for the climate change. So we have a big temperature increase. That temperature increase is leading to increased water losses, mainly through evapotranspiration rates. And therefore we have high crop water requirements. Therefore, we have to supply more water, and we are in the area where water is already a scarce resource, and it's becoming even more scarcer with climate change. So in the context where we have all these problems, it is realize it is of utmost importance to optimize water consumption and increase water resources available for agriculture. In the last years, our group is working on different areas of water management, as I said. So we work on optimization and modeling of agricultural water resources. That area is focusing mostly on precision irrigation and the estimation of the water needs for agriculture. So we have to change the concept. The concept now is to put water, and if we lose some water, then it's okay. It's not okay since we don't have water, so we have to estimate exactly what kind of water requirements we will have in different months of the year based on the crops we are growing. To reduce water consumption, we can also use precision irrigation. So giving the crops exactly the amount it needs in the given moment. Since water resources are scarce, we can increase available water through reuse of treated wastewater. Treated wastewater is an important resource. It's available throughout whole year, and it also has a big added value that are the nutrients and different elements present in treated wastewater. So it's an important resource, and in the whole world we are basically now trying to turn waste into a resource. And finally, we are working also on improvement on quality of surface water bodies. So we have lakes, we have rivers, we have different water bodies that are being polluted through agricultural activities. So we are trying to reduce that pollution. All these activities, we are doing them through different we are working a lot on international projects. We have also some smaller national and regional projects, but we are working mostly on European projects that are focusing on these different areas. So now, if you agree, I will try to focus on different projects just to give you a touch of the research we are doing in these areas. So if we start with the first pillar, optimization and the use of irrigation water, as I said, we have to estimate well the amount of water that we will need for crop growing, and we need to reduce water use for agriculture. So one of the projects that is dealing with this topic is SWAMP, smart water management platform. It was a European project that ended 2 years ago, and it developed Internet of Things platform that is doing smart water management for precision irrigation in agriculture. What we did in this project, or what this platform was made to do, is to consider all the data that are important to estimate water requirements for crop production. So we took into consideration different data inputs. The weather is really important aspect, since it gives us the idea of the rain or the temperature that are influencing water requirements. The platform is also considering soil moisture. That is again important input in this context. So through all these data sets, the platform is calculating how much water needs to be distributed in different moments. The project focused on different test sites in different areas. In Italy, it was near Bologna, where we had a test site. Different sensors were installed to monitor soil moisture, to monitor weather conditions, and to test this platform in the study site. Then we have another current project that is Bonex. It's a Prima project. Prima is a foundation that is focusing on the Mediterranean area. Italy is part of the Mediterranean, so we are working with this project. The focus, the objective of the Bonex project in Italy is to optimize irrigation district water balance in the terms of quality and quantity. So we are trying to limit losses in the water distribution system. So we have a network of surface channels that distribute water to the final users. And we have certain water losses in this distribution network. So we are trying to reduce these losses and to improve water use efficiency. Through reducing losses, we can also reduce freshwater abstraction from surface water bodies. So in the Bologna area, in Emilia-Romagna, that is a region of Italy where Bologna is located, we are taking water from the north of Italy, Po River, and we have a 120 kilometers long canal that is taking water from the Po to these areas. So we have to reduce freshwater abstraction, and we have also energy consumption connected to this. We are in the plain, so we have to use the pumps to distribute water in different areas, and the use of pumps, of course, consumes a lot of energy. So we have to, through reducing freshwater abstraction, through reducing water losses, we are also reducing the energy consumption. In the Bonex project, we are focusing on a 25,000 hectare irrigation district. So it's a big irrigation district where we are studying different aspects. We are considering different areas of the optimization of water balance. So we are considering the water fluxes to and from the irrigation district. And as I said, we have different specific objectives. So one of them is to reduce losses through evaporation or infiltration from the surface water network, to decrease energy consumption, to assess the effect that nature-based solutions so we have in these irrigation districts, we have different nature-based solutions and different wastewater treatment plants that discharge water into the surface water network. And we wanted to assess the effect that these nature-based solutions can have on water quality improvement, and also how treated wastewater discharge influences the irrigation water quality. And we are also considering a novel moving technique to improve water quality. So basically, we are trying to reduce the rate at which riparian buffer is being harvested to increase its role for water quality improvement. This is the district that we are focusing on. So as I said, it's almost 25,000 hectares. In this irrigation water district, we have different water inputs. We have surface water inputs, but we also have, as I said, different wastewater treatment plants that discharge water into the surface water network. So we have indirect water use, but we also have different outputs. Well, to be precise, we have one output from the district. If we are considering water balance of the irrigation district, then of course we have to consider different components. So we have to focus on losses through evaporation and filtration, but then we have to consider also precipitation as an input. We have to consider input from the surface water bodies. We have to consider inflow from wastewater treatment plants. We have to consider irrigation water output. And we have also, what is curious about this irrigation district is that we have a lot of wetlands. A lot of wetlands that can contribute to improving water quality, but they also consume water. So to be able to close the water balance of the irrigation network, we have to consider all these components. In the same irrigation district, we are currently doing a study of potential and feasibility for urban wastewater reuse. So we are trying to evaluate what kind of potential treated wastewater has for satisfying irrigation water requirements. So we are assessing different irrigation wastewater plants from different points of view. And we are also developing a risk management plan for the treated wastewater reuse. I'm not sure if you're aware of that, but in 2020, the European Commission approved, European Parliament actually adopted the new wastewater reuse guidelines. So that is giving clear instructions on how to conduct water reuse in different areas and what kind of minimum quality treated wastewater needs to have to be able to reuse it in agriculture. One of the specific requirements of this European regulation, is also to develop a risk management plan for each area where we do water use. So we are also doing that in this irrigation district. This is a bigger area, so 140,000 hectares, of which 90,000 hectares can be irrigated. In this area, we have 31 wastewater treatment plants of different size, of course, that were being selected based on their point of discharge. So if they're discharging water inside or near irrigation district, and we also considered the wastewater treatment plants with a capacity higher than 2,000 population equivalents. So we have in this area, we have well more than 31 wastewater treatment plants, but some of them are really small, around 1,500 population equivalents. That is, you will agree, really low water volume, so we are not considering them in this study. And we also have some wastewater treatment plants that are discharging water currently outside of the irrigation district, so we are also not considering them. This was the first step of the analysis. We also evaluated how much this treated wastewater can contribute to irrigation water requirements. And we also classified the treatment plants that are suitable for water use. Suitable meaning that it is discharging water near the irrigated areas, suitable in the terms of volume, as I said, and especially suitable in terms of water quality, of treated effluent quality. These treatment plants are working in different ways. So they have different water quality, different qualities of the effluent. According to the new European regulation, we have four classes of treated wastewater. Class A is the best, Class D is the worst, but all of them are can be used to irrigate certain crops. We defined in these 140,000 hectares, we defined different reuse areas. In the end, we defined 16 reuse areas that were defined based on their input nodes. So where water abstraction point is, how is the context of surface water network. So how long is it? How well distributed is it? And also where is water discharge from these reuse areas. Once we defined these reuse areas, we also did different actions so we tried to match wastewater treatment plant effluent quality and the requirements of the reuse area. Based on that, we did different potential scenarios. So, for example, we have a wastewater treatment plant that is discharging effluent in the C class, but our reuse area crops need B quality. So how can we match the requirements and the available resources? And we also define different protective measures and barriers that can be used to increase safety of treated wastewater use. We did the risk management plan as I said, for one of these reuse areas. The particular point of interest for this reuse area is that we have a storage basin. So we also try to see how this storage basin can affect water quality. This is the risk exposure and risk management plan. So it's in Italian. I'm sorry, but I will explain it to you. So we have different environmental and human health risks. So when we consider human risk, then we have to be aware of the workers that are working in this area and that can be in contact with treated wastewater. So the farmers are of course one of the potential affected groups, but we also have to consider local community, so bypassers or the workers that are dealing with water distribution. So we have to consider different areas, different ways how they can be exposed, and how their health can be affected. Also, in this area, we associated water quality class with the needs of irrigated fields. We did the study from 2019 to 2023. We have data for all these 5 irrigation seasons. So for each season, we studied the surface that was irrigated and what kind of crops were irrigated. Based on the crops that were irrigated, we concluded what kind of quality was necessary, treated wastewater quality was necessary to eventually irrigate these crops with treated wastewater. We also did risk assessment for a much bigger area. This is near Rome, actually, where we have in total 73 irrigation districts and 2 sources of supply, 2 rivers that were Tevere and Arone. This is the scheme of the irrigation district where we did this risk assessment. We have wastewater treatment plant that is producing treated wastewater. We have different channels that are used to distribute this water, and then we have also different storage basins where this water can be eventually stored and then used afterwards. We considered for this area, we considered two risk assessment matrices. So we dealt with human health risk assessment and environmental risk assessment. When we talk about human health, then we have to consider different workers in the area and how they can be exposed, as I said. But we also have to consider how environment can be exposed to treated wastewater. So different environmental components such as surface water, groundwater, and soil. So in the case the treated wastewater quality is not that good, we have to consider how it can affect these environmental matrices. For each reuse area, we assessed different hazardous events that can occur, what kind of consequences they have, but we also considered calculated risk based on the likelihood of occurrence and severity of the hazard. So likelihood of occurrence is how likely is this hazard to happen, and the severity is of course how important consequences can be. And based on that, we calculated the final risk. When we talk about environmental risk assessment, we have to consider another variable, that is environmental sensitivity, or in other words, how environmental components that we consider can react to different ways of pollution. If we move now to wastewater treatment and effluent reuse, also in this kind of topic, we have different projects. Fit for Use was a big project that we had. It finished 3 years ago. And the main objective of this project was to provide safe, locally sustainable, and accepted ways of water supply for the agricultural sector by exploiting non-commercial water resources. When we talk about non-commercial water resources, we consider treated wastewater and saline water. So in this project, we focused on different treatment technologies, how the use of these non-commercial water resources can affect agricultural production, and finally, what kind of regulation we have in this area. So we had different pilot plans that were used for the treatment and quality improvement of non-commercial water resources. We developed a simulation platform that was predicting performances of different technologies for the treatment and how they can react in the conditions that we have not tested them in. Then we did tests with treated water used for irrigation to see what kind of effect it has. We worked also on risk management, as I said before, and we dealt also with the stakeholders. So we developed a platform that can be used to connect different types of stakeholders and to collect their opinions on the topic. We dealt a lot with nature-based solutions, constructed wetlands. You see a small pilot plant near Bologna that we had that aimed to test different kinds of constructed wetlands to improve quality of wastewater, domestic wastewater. We consider different substrates, different combination of the treatment units, and different operating parameters. So, for example, hydraulic loading rate and hydraulic retention time that are very important when we talk about constructed wetlands performance. We also tried integrating constructed wetlands with intensive solutions. So, for example, upflow anaerobic sludge bed or the membrane bioreactor. So we try to integrate different solutions to improve performance, so to achieve better quality of effluent, but also to lower the environmental footprint of these technologies. You can see here the web platform that we developed to be able to monitor the pilot plant remotely. Different pumps that, so basically we can click here on different pumps to see how they're working, to turn them on, turn them off. We can change their water flow and so on. The simulation platform that I talked about, so it's trying to simulate the performance of different treatment solutions. We tested different treatment solutions, but of course we didn't test them in different environments. So this negative aspect was overcome by development of simulation platform, where we could combine different treatment trains to see how they can perform in different areas. We developed risk management for different areas that were considered in Fit for Use project. I already talked about risk management, so I wouldn't. I don't want to spend a lot of time on this topic, but we have different case studies. Here you can see, for example, case study in Greece, where olive trees were irrigated with treated wastewater. So we considered different risks that can occur in that practice. The public consensus is really important when we talk about reuse of treated wastewater. So we all know about yak factor, for example. So we try to use the concept of citizen science and citizen sensing to improve public opinion on water reuse. So one of the tools we used for that was multi-stakeholder platform that, as I said, was used to connect different stakeholders. We also did different events. In our experience, it's really important to organize these round tables or webinars where we can give to the public the right information in the right time about the treated water use. We also developed experimental platform near Bologna, where we did irrigation with secondary and tertiary treated wastewater to see what kind of effects they had. And we irrigated tomato and peach. Peach was irrigated with secondary treated wastewater. Tomatoes, since they are more sensitive crops, were irrigated with tertiary treated wastewater. So the objective of this trial was to develop irrigation systems that can be used for irrigation with treated wastewater. We also wanted to assess fertigation potential of treated wastewater, so to see how much of crop nutrient needs can be satisfied through concentration of nutrients that is present in treated wastewater. And we also use this platform to assess the effects that water use can have on soil, crops, and whole soil plant system. In this platform, we could monitor the nutrient needs in real time and the nutrients provided to the crops through irrigation water. So we considered concentration of nutrients in irrigation water. The platform was able to calculate how much nutrients these crops need. So these remaining part was added through through the special pumps and algorithm calculation. We also have a platform to deal with this experimental site remotely. So we can see here different water quality data to be able to calculate how much nutrients we need to add. We have this nice calendar that we can select the days when we want to do only irrigation or irrigation with fertigation, so adding of nutrients through fertilizers. So we estimated how much nutrients requirements can be satisfied through treated wastewater. So we had different data, but as you can see below, the macro element saving can be quite high. So for basically treated wastewater, it can satisfy up to 1/3 of nitrogen requirements by the crops. We also tested different irrigation systems. So basically, treated wastewater can close can contribute to development of biofilm in irrigation drippers. So we tested these effects through assessment of distribution of uniformity of distribution of irrigation water. We are trying to consider also crop contaminants of emerging concern that can be present in reclaimed water and to see what kind of effects they can have on crops or soil. This is relatively new part, so we are developing methodology for this kind of assessment. We are testing different kind of irrigation drippers, emitters to see how they can resist through eventual biofilm formation that can be caused by use of treated wastewater for irrigation. Then we have relatively new project that is Boostin that is trying to implement a successful strategy to promote water use in different European countries. So, for example, in Spain and Italy, we are focusing on domestic wastewater use in agriculture. In Greece, it's industrial water use, while in Bulgaria, for example, it's mining wastewater recovering and the use of this mining wastewater. In Italy, we are focusing on Emilia-Romagna region where Bologna is located. Emilia-Romagna is a really important agricultural production spot. So in Emilia-Romagna, we're producing almost 16% of the whole Italian agriculture export. So agriculture is a very important is a very important sector for Emilia-Romagna. So we are trying to identify different water water solutions for the circular economy to promote wastewater use and to increase knowledge on water use of different stakeholders. And finally, focusing on water quality improvement. So, as I said, agricultural production can affect water quality in negative ways. So we developed different solutions to deal with this potential agriculture pollution. We have project FarmWise, that is European project currently running that is aiming to transform European agriculture sector by implementing of different solutions, also focusing on artificial intelligence. In FarmWise, we are a very big consortium, so we have different European countries from Italy to Spain to Sweden Poland, and so on. We have different test sites in these countries. The Italian site is located near Bologna, where we are focusing on sensors, low-cost sensors for measuring of water contamination. These sensors are really low cost and simple to use, so we believe it can be they can be also used for citizen science promotion. The Water Agri project is a similar European project that is trying to introduce solutions that can be used for water retention and nutrient recycling in agriculture to make agricultural production more sustainable. What we did in this project, we tested different kinds of constructive wetlands to improve water quality. And to close the circular approach, we also recovered the biomass from constructed wetlands to see if they can be used to produce compost for that can be used later for agricultural production. We focus on different types of constructed wetlands, so horizontal flow, surface flow, that can have different benefits for water quality improvement, but we also considered biochar. Biochar, as we know, is organic material that can be used to absorb nutrients from water, and since it's organic material, that it can be degraded and used as a soil amendment. These and other experiments we are doing in the Marsiglia experimental platform near Bologna, that is 12.5 hectares agricultural farms, and we are focusing mostly on constructed wetland that is in this. It's a full-scale constructed wetland in this farm that is being used to treat drainage water, agricultural drainage water. It's a full-scale system, as I said. I'm not sure if you can see my mouse, but here in the low left corner, you can see the bird view of the system. And this white spot here is a car, so you can see how big it actually is. How this system is functioning, we have here with the blue arrow, we have drainage channel that is collecting drainage water from the farm. In the red square, we have two pumps that can be used to pump water inside the system. So these are the pumps. They take water from the channel and send it directly to constructive wetland. Constructive wetland has a central control unit that can monitor different parameters, but that can also take samples of inflow and outflow water, so that we can analyze this water for water quality. This is the inflow in the system, so it's like a fontaine. It's really nice when it's functioning in the full capacity. Then we have four meanders, so water is following this path, and finally we have water outlet through gravity. We do experiments with this system since more than 10 years. In particular, we analyzed 2 years, 2018, 2019, in specifics to see how the system functioned. You can see different water quality parameters and how the system was operating. So you can see that it could remove around 50% of chemical oxygen demand from the inflow water. It can remove about 70% of suspended solids, nutrients, and so on. So we are sure that this system is functioning well. We also tested this system for a removal of different pesticides. to see how the system can deal with emerging contaminants. And we received also really nice results from this study. So basically, we observed a mean dissipation of 50% in less than 7 days. Finally, we have CardioMed project that is currently running. It's focusing on the Mediterranean area again through different pillars. It has different demonstration sites. In Italy, we have demonstration site in the island of Sardinia. Where we are focusing on different agriculture solutions. So we are doing crop rotation, repairing buffer to improve water quality, constructing wetland, and so on. So it's a farm, 4 hectare farm that where we are applying different solutions to improve sustainability of agricultural production in this farm. So in conclusion, we can say that water sector needs to be more resilient since we have climate change and negative effects of it. But we also have anthropic pollution that is lowering sustainability of agricultural production. The digitalization is one of the key issues. So we need to apply new digital tools and artificial intelligence to improve sustainability of agricultural sector. Of course, all these solutions that we can develop and apply is nothing without stakeholder acceptance. So we have to involve stakeholders in each step of the way to ensure that the solutions that we are developing can be used to satisfy their needs. All these aspects are also considered in the Green Deal of European Union. I'm not sure if you're aware of it, but European Commission and its President von der Leyen introduced this Green Deal that is trying to make Europe carbon neutral by 2050, but it has a series of different topics, and one of the topics is also sustainable agricultural production and healthy water resources in Europe. So that's it from my side. I tried to cover different aspects. I hope you received some of the messages, and if you have any questions, I will be more than glad to reply.